audio speaker such as this one consists of a diaphragm, often with a central dome-like structure, mounted to a steel frame by a flexible surround that allows longitudinal displacement of the diaphragm like that. On the back of the speaker are one or two permanent magnets. This magnetic ring here would be accompanied inside the steel enclosure by a disc-like permanent magnet. Between the disc and the ring would be a paper or plastic tube with many coils of wire wrapped around it, called voice coils. Those voice coils are held in place firmly by this ring-like pleated structure called a spider. And while it holds the voice coils laterally, quite rigidly, it allows the longitudinal displacement that's necessary so that when the input current to the voice coils varies, the electromagnet of the voice coils causes their position to change longitudinally with respect to the permanent magnets, and we get sound emerging from the front of the speaker. Now, if we could cut away the diaphragm, the steel frame, and replace these bulky ferrite magnets with stronger and much lighter neodymium alloy magnet, we would have something called an exciter. Here's our steel enclosure. Here's our central neodymium magnet. And here's our pleated spider holding in place a plastic tube with the voice coils on it, allowing it to dislocate longitudinally with altering current through these input wires. Instead of a paper diaphragm, we have a ring of very high bond 3M double-sided adhesive. If you pull off the protective paper, you can mount this to any flat surface, such as a store display, which in conjunction with an appropriate trigger might announce when a customer walks past a slogan such as "Spice it up," using the entire display surface as the vibrating diaphragm. Now, with respect to orthosonic lift by radial deflection, I have demonstrated using a standard speaker design in conjunction with a flat wing, usually having a central port cut for the sound to emerge through. And when that's in close approximation to a reflecting surface, the sound waves are diverted across the wing so they're vibrating air in every direction radially, and the motion of air on the upper surface compared to still air underneath resulted in our orthosonic lift. But I have been thinking it might be possible to incorporate the function of the lifting surface and the speaker diaphragm together in a single wing structure. And with that in mind, I cut this oak tag disc, weighing 4.3 grams and having a diameter of 6 inches, from an ordinary file folder like this one. Note that I did not cut a central port, as I intend to attach one of these exciters to that region, manufactured by a company called Highwave. These exciters range in continuous power handling capacity from 1/2 watt to 2, 3, 5, 10, and 30 watts, and in single unit retail pricing from about $2 to about $20. But a variety of exciters called shakers goes much larger, costing hundreds of dollars. They can range over 5 kilograms in mass and handle well over 1,000 watts. Companies like Disney attach them to theater seats so that viewers can experience the simulated vibrations of a rocket taking off to Mars, for example. I, on the other hand, will arbitrarily choose this modest 3-watt exciter, giving me the option to increase if more raw power is required, or to drop back to 2 watts, where the power-to-mass ratio doubles to 0.21 watts per gram, as compared to 0.1 watt per gram here. Now, it will be the purpose of this experiment to examine the performance of this exciter in conjunction with our dual function wing diaphragm in the application of orthosonic lift by radial deflection. So here we have our 6-inch unported wing with a centrally mounted 3-watt driver. It's rated at 8 ohms impedance, and it's important to check on the back of the power meter that the switch is set to match at 8 ohms rather than the 4 ohm setting here, and that's looking good. While we're here, let's check the mass of our system. And that's just a little over 34 grams, 34.3 grams. And I'll move the system underneath our deflector, which this time is a clear glass plate that lets a little bit more light on our experiment. I have it outlined in blue tape so I remember it's there, and it protects my fingers. This will be the tripod where we set the camera, but first let's check our meters and settings. We're going to be at 240 cycle per second sine wave, and we'll be using the power meter at the 2-watt range, this lower scale, and we expect the needle to move somewhere between the 1/2 watt and 1 watt indications, and that will mean that 3 LEDs will be lit for a 1/2 watt, and if you see 4, we've hit 1 watt. So we'll put the camera in the tripod.